Welcome to this episode of Georgia Highlands College Chemistry Podcast. In this podcast, we will be discussing chemical reactions in aqueous solutions. But first, we're going to learn how to write chemical equations that describe reactions in aqueous solutions. In this case, we're going to be using three types of equation. The first type is the formula unit equation. In the formula unit equation, we show complete formulas for all compounds. So, for example, in the reaction of aqueous silver nitrate with solid copper to form solid silver and aqueous copper nitrate, we have the molecular formulas of all compounds. Then our second equation is the total ionic equation. In the total ionic equation, formulas are written to show the predominant form in which each substance exists when it is in contact with aqueous solution. We're going to use brackets to show ions that come from a common source. This is not necessary all the time, but it's just a convenient way and a shorthand way to show this on our paper. For example, aqueous silver nitrate exists as aqueous silver ions and aqueous nitrate ions. Solid copper and solid silver exist in the solid state. And then aqueous copper 2 nitrate exists as aqueous copper 2 ions and aqueous nitrate ions. This is because all nitrates are soluble. We note on this equation that we have nitrate ions on both sides of our reaction arrow. In this case, the nitrate ion is known as a spectator ion. When we go from our total ionic equation to the net ionic equation, we remove these spectator ions from the equation. So, for example, we remove our nitrate ions, and we're left with what is actually changing in this reaction. Aqueous silver ions react with solid copper to form solid silver and aqueous copper ions. Net ionic equations allow us to focus on the essence of a chemical reaction in aqueous solutions. On the other hand, if we were dealing with stoichiometric calculations, we frequently must deal with formula weights, and therefore it is more convenient to use the complete formula of all species in our calculation. So how do we know when to write something in the ionic form or the molecular form? We always write things in the ionic form if it dissolves to a major extent in solution. This will be for strong soluble acids, our 7 strong acids, our 8 strong soluble bases, and our soluble salts. We know the soluble salts because we know the solubility rules. In our summary, we're going to look at a molecular equation of aqueous hydrobromic acid reacting with aqueous potassium hydroxide to form aqueous potassium bromide and liquid water. To go to the total ionic equation, aqueous hydrobromic acid exists as aqueous hydrogen ions and aqueous bromide ions because it is a strong acid. Likewise, the strong base, potassium hydroxide, would exist as aqueous potassium ions and aqueous hydroxide ions. Potassium bromide, this would exist as aqueous potassium ions and aqueous bromide ions because all group 1 salts are soluble. And then liquid water exist as liquid water. Things written in the solid phase or the liquid phase are written in the form that we're given. And then when we move our spectator ions to go to the net ionic equation, we can end up with aqueous hydrogen ion reacts with aqueous hydroxide ion to form liquid water. We have removed our spectator ions, the bromide ions, and the potassium ions. So these three equations, the molecular equation, the total ionic equation, and the net ionic equation, have their various uses. Again, we usually use the molecular equation for stoichiometric calculations and to give us an overall picture of what is going to happen. And then the total ionic equation is a truer representation of how these chemical species exist in aqueous solution. And then finally, our net ionic equation is a representation of a Cliff's Note version showing us exactly what has changed in this chemical reaction. Thank you for listening to this episode of Georgia Highlands College Chemistry Podcast. We hope this episode has helped spark some interest and excitement in chemistry. We look forward to sharing more chemistry podcasts with you in the future.